Okay, yes. So a little bit of a disclaimer is that, oops, good start. A little bit of a disclaimer is I want to take this talk to just kind of describe vaguely using pictures one kind of small phenomenon that takes place in tropical geometry and say a little bit about it. It's meant to just kind of, largely try to get people interested. I'm going to not make any, I think I'm going to essentially not make any precise statements. I welcome questions, but I would ask that the experts in tropical geometry who are going to object to many of the things that I say, wait to yell at me until after the talk is over. Yeah, so and I mean, okay, yeah, let me get started. So, so first of all, what is intersection theory? Period in algebraic geometry. It is the study where you try to understand intersections of subvarieties of some ambient space. Intersections of varieties without actually computing them. Okay, because computing the intersection of two subvarieties usually means simultaneously solving their defining equations, and that is hard algebraically to do, but sometimes you can say a lot without doing that. So for example, this is maybe the classic example of this phenomenon is Bézout's theorem, okay, which says that if I take two plane curves, say x1 and x2 in P2 with degrees d1 and d2, okay, then with some mild assumption, as long as they don't share any irreducible components, the intersection of the two consists of d1 times d2 points, as long as you kind of count with multiplicity. Okay, so something like if you have two curves that meet at a point of tangency, it should count for multiple solutions, multiple points of the intersection. Okay, so without computing the actual intersection, you can say how many points it contains. And it's important here that we're working in P2. You might imagine in A2 that if, say, you're working with two lines, then it matters whether those lines are parallel, in which case they don't intersect, or not parallel, in which they intersect in a single point. And so there's this kind of rule of thumb that says that you need the ambient space, the ambient variety, to be compact, okay, as P2 is. Otherwise, you might have these kind of intersection points that disappear off to infinity and you forget about them. Or possibly you just kind of, you need to be very careful. And of course, what that means depends on the context. Okay, however, what I want to talk about for the rest of the talk is a setting where you get a lot of nice intersection theoretic structure working on something non-compact, okay? Namely, I want to consider intersection theory in algebraic tori. This is a case where there's lots of nice structure. So by algebraic tori, I mean, well, let's work over C and say we're working in C star to the end. Okay, so over here, you know, we had, I need to start drawing pictures. We had two plane curves, which I want to actually be slightly careful in my drawing. We had two plane curves. Maybe one of them looks like this. Okay, this is my x1, and the other one maybe looks like this. That's my x2. And before I was considering this picture inside of P2, so there was a line at infinity. But now I want to try to do the same intersection calculation and work inside of the torus. So I'm taking this picture. I've got no line at infinity, and I'm also removing the axes. So I take puncture at these 3 points. Well, puncture at the 2 axes. Okay, and I'm going to allude to several things that Felix just said in the last talk. The way that you get a bunch of structure in this problem is by doing this thing called tropicalizing. So I've got 2 curves inside of a 2-dimensional torus. I can tropicalize them. If I had a little bit longer, I would tell you how you actually do that. It's not a very complicated procedure, but instead I'll just draw a kind of plausible, and again, experts please don't yell at me, tropicalization of the 2 curves that I've drawn here. So now I'm going to draw something inside of R2, and I will keep them color-coded. And here is my, okay, these are balanced polyhedral complexes with rational slopes. So here's my trop x1, and here is my trop x2. Okay. And the way that you intersect things using tropical geometry is you look at these tropicalizations, you look at their intersection points. I've got here, 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 and here. Okay, and all of these other lines go off to infinity, so there aren't any others. And you add up for each intersection point something called its tropical intersection multiplicity, which again it's easy to describe, but in the interest of time, I won't say how you get it. It's some determinant. And in this case, all of these have multiplicity 1, except this one here has a multiplicity 2. And if you add up those multiplicities, you get 6 points. Okay? And that essentially should tell you, and it modulo the fact that I'm being super imprecise about everything here, it does tell you that your original 2 curves intersect in 6 points, which maybe you can't see all of them in this picture, but that's okay. Maybe some of them have complex coordinates. Okay. On the right, there are 5, but this one counts with multiplicity 2. And I haven't told you why, but it has something to do with the angles at which these 2 lines meet. Yeah. Yeah, and you know, I should have said at the beginning, you know, I'm saying all of this vague stuff in kind of the hope that maybe some of you will come and ask me for precise statements later. Because there's a lot more that you can explain with just a little bit more time. Okay. Other questions? Yeah. Okay, and I also want to give you, again, a kind of approximate geometric, not explanation exactly, well, yeah, kind of explanation of what is going on here. Why does this work? Why can we do this kind of polyhedral calculation and have it give us the same thing as we actually wanted to compute in the first place? The vague reason is that what we're doing here is we're translating x2 along some subgroup, okay, of the form, this form. Okay, so this gives me a subgroup of my torus, and I can just translate x2 by multiplying by that subgroup. And I, maybe have to choose my m and n correctly and maybe large. And if I do this, and I take t to 0 in the limit, so then what am I going to be doing? I'm going to be taking x2 and kind of shrinking it down, okay, to the origin almost. Except if I'm, depending on how I do it, I might have some kind of very simple, like if m and n were 1, then I might get some lines through the origin, like a union of lines through the origin in the limit as t goes to 0. And so generally, as t goes to 0 and I take this kind of limit, x2 is going to turn into some very simple subvariety, something that is very easy to compute the intersection with x1. And so then it becomes easy to compute x1 intersect t x2, the translate of x2, to compute that limit as t goes to 0. Again, it was very vague, but this is the sort of reason why this, I mean, it's the sort of reason why all of this tropical intersection theory actually works. And I've done an example here with n equals 2 and with two curves, but something just like this works in arbitrary dimension. Okay. I want to say something that's just very slightly more general than this, because a lot of the interesting intersection problems that we want to study are not happening in a torus. Maybe they're happening in something like MGN bar, something that is more complicated. And there's a more general version of this. So I should say, since I've been leaving out attributions, this whole idea, I think, originates in work of Bogart, Jensen. Someone else can jump in if this actually goes back earlier. Speyer, Sturmfels, and Thomas. This idea of you can intersect or you can tropicalize and then intersect and you get the same answer. Yeah. Potentially, yes. You do have to worry about that. And so really, we might not get the actual tropical intersection, and we might not get the correct intersection number. We still have to, there's a little bit of interpretation to do once we've calculated this thing. But depending on kind of their geometry, you may or may not see it in the tropical picture. So yes, I can say things about what the tropicalization is. I would like to wait until after the talk, if that's okay. Because I also have other things that I want to say. There's a... Yeah, well, there are you won't be able to glean from this picture because, in fact, in order to get these tropicalizations, I would need to start with curves defined over a valued field, a non-trivially valued field. Otherwise, I should get fans here. There are several equivalent ways of saying how you get the tropicalization. Some of them come from algebra, some of them come more from geometry. But I don't want to say, yeah, sorry. Okay, so more generally, and this is, I think, a kind of version due to Osterman-Payne, is a version of this setup that doesn't require you to be doing the intersection in a torus, but allows you to do it instead in a subvariety of a torus. So your ambient space is maybe something that is instead a closed subvariety of a torus. So let's maybe call it Y, and you want to intersect a couple of subvarieties of Y. And I don't know if I can draw very interesting subvarieties of this variety, but whatever. Oops, that should end there. Yeah. Okay, but I do want to draw the picture because I'm going to use this picture again. So again, we can take the tropicalization now of our x1, our x2, and our y, and we get a picture that, if I'd had time, I would have drawn before the talk started, but I will do my best to draw a three-dimensional picture without messing it up too badly now. Okay, so trop y might look something like this. Y is two-dimensional, so we get a two-dimensional polyhedral complex as the tropicalization. And inside of it, this is an inclusion-preserving process, so we're going to get a couple of one-dimensional polyhedral complexes inside of here. Okay, so there's trop x1 and trop x2, which, again, these are all, so far from being exact anyway that it doesn't matter too much how I draw it. Okay. But what Osterman-Payne says is that you can still calculate the intersection of x1 and x2 by calculating the intersection in trop y of trop x1 and trop x2. You count them up with multiplicities. I've got a couple of intersection points I see here. And everything is fine. Everything works just the same, provided that this intersection takes place inside the smooth locus of trop y, right? So it should avoid the kind of place where these polyhedra meet each other and happen at something that looks linear. And then you can kind of take that plane and pretend that it's just your R2 from the previous setup. So it works if trop x1 intersect trop x2 is inside the smooth points of trop y. Okay, and so I think that this is just like a very nice little story in itself. Something, I mean, one can start to do immediately really fun examples. Like you could take trop x2, you could translate it a little bit in this picture, and you could check, after I tell you how to calculate the multiplicities, that if you translate it somewhere else, it's not at all clear from the picture that you're going to get the same number of intersection points counted with multiplicity. And it follows from this balancing condition that Felix talked about that, in fact, you do. Okay, and so this is, I think, kind of the original story of tropical intersection theory. But what I want to talk about with the rest of my time, and when did I start exactly? Do you know? Okay. Oh, that's generous. Okay. What I want to talk about with my remaining 10 minutes is something else that you can do with tropical intersection theory. So it's a different kind of problem that we can solve using a very similar setup. Okay. And I'm going to illustrate it essentially just with pictures. And some of them I'm going to reuse. So yeah, forget about that blackboard for now and say, okay, so it's a similar setup to what we have here. We have a closed subvariety of a torus Y. I need only one subvariety of it now. So I've got my Y, which lives inside of our torus. I've got my tropicalization of Y, which is this polyhedral complex in Rn. Okay. And I want to work in the special case. I'm going to delete all of the text now because I'm going to redo all of it. Okay. Okay. I want to work in a special case where where trop Y is a fan. Okay, and fan just means that if that it's invariant under multiplication by positive real numbers. So under the action of the positive reals. Okay, so like the one that I've drawn here is a fan. If this is my origin, then, oh no, that's not my origin. If this is my origin, then, and all of these planes extend out infinitely, then I can multiply by a positive real number and the picture doesn't change. Okay. Now in that case, we get for free some structure. Okay, so if trop Y is a fan, then many of you know that to a fan we can associate a toric variety. Okay, so we get a toric variety maybe I'll call it Z, which compactifies the torus, the ambient torus that Y lives inside of. And we can take the closure of Y which is a compactification of Y bar inside of this toric variety. So we're taking our subvariety Y and we're gluing on a bunch of stuff at infinity, okay, to get a nice compactification in a way that is kind of like canonically given to us by this fan. And just like in MGN bar, you have now kind of a stratified structure of Y because a toric variety has a stratification of all of the stuff you've glued in at infinity, and you can kind of pull back that stratification to Y bar. You get strata, and they correspond the strata correspond to cones of your fan trop Y. Okay. So I've got kind of, in this picture, I've got 6 two-dimensional cones, and namely those 6 planes or bits of planes, and I've got 4 one-dimensional rays also, and each of those objects is going to correspond to a stratum. Right, okay, and so this setup, this is what's called a tropical compactification of y because it came from the tropicalization of y. And they were first studied by Tevelev and are useful for many things. This assumption I made about trop y being a fan is actually not a very special case. I mean, I'm avoiding saying the words valuation and valued field, but as long as y is defined over a trivially valued field, this is always the case. Okay, so now let me tell you what we're trying to do in this actual problem. I said that there's a problem that we're trying to solve here. And the problem is, well, inside of my y, I've got a variety, an x1. Guess I might as well just call it x now. I want to think of that as not just I want x to not just be a single variety, but a family of varieties, parametrized by some t. Okay, so I want you to think for each t, I get something like this, but as t changes, it kind of moves around. Okay. It turns out that to such a structure, you again can associate a tropical thing. So this will be trop xt. And the problem is to be able to compute the limit as t goes to 0 of xt. So this is some sub-scheme or really cycle in y bar, okay, using tropical geometry. So using what we know, namely the tropicalization of xt. Okay, and it turns out that this is possible. So I'll make a different statement in just a second, but this is possible under certain assumptions. There are assumptions like, well, xt, you don't want it to just be sitting in one place. You don't want it to be constant in t, because then the tropicalization will be something very boring. You want it to really be degenerating away to the boundary strata of y bar until it just breaks up into a union of boundary strata. Okay. And so let me tell you a kind of heuristic and the only slightly more precise version of that heuristic. So the way that one should be able to solve this problem, if you kind of think for a while about the geometry of what's going on when you take these tropicalizations, all of this stuff that I'm not telling you. The geometric heuristic here is that this limit, as t goes to 0, of xt should be determined by trop x1 by an intersection, a tropical intersection, the sort of thing that we actually know how to work with. So trop x1 intersect, this is the one skeleton of trop y. Okay, so in this picture, we are actually going to add in an x2. What we should do is we should take our trop xt, sorry, I wrote trop x1, but I meant trop xt, and we should intersect it with all of the one-dimensional cones of trop y. Okay, so the rays in this picture. There's a kind of, again, there's a heuristic argument that tells you that this is somehow, these intersection points here are, like, correspond to irreducible components of this limit. And which irreducible components? So notice we've got a couple of intersection points there. There's one, and there's one. Each of these intersection points is in some ray that corresponds to a boundary divisor in y bar, and those two boundary divisors should be the irreducible components of this limit. Okay, unfortunately, we have a little obstacle here, which is that if we want to compute this limit as a cycle, we need to know the multiplicities, the tropical intersection multiplicities of these two intersecting things. Okay, but what I told you earlier is that tropical intersection theory only works when these intersection points happen at a smooth point of the ambient trop y. Okay, and these things are never going to happen at smooth points because, I mean, by construction we've said that they are in the one skeleton, which is and generally one would be replaced by whatever the complementary dimensional skeleton is here, and I'm just working in something in ambient two-dimensional. So obstacle is that the intersection never happens at smooth points, essentially. Okay. And so okay, I'm out of time, so let me stop with just a kind of stating the vaguest version possible of the result, which is joint with Sean Griffin, Jake Levinson, Rohini Ramadas, myself, is that you can fix. So you can fix this problem and calculate the multiplicities correctly. And the way you do it is you look at one of these points and you zoom in to a little neighborhood of that point, and then you take the thing that's causing the problem, the blue segment here, and you perturb it a little bit into one of the adjoining cones. It doesn't matter which one. So you can move it up into this two-dimensional cone, or you can move it out into this two-dimensional cone, or you can move it this way into this two-dimensional cone. And you compute the tropical intersection there. And that's you've gotten back into the situation where things are actually well-defined. And it's independent of how you do it. And then that allows you to finish the calculation and calculate this limit.